Hi everyone, my name is Michael Hyatt. I'm a solutions architect with Elastic. I've been with Elastic for slightly over 3 years, and um, I'm based in Melbourne, so hunkering down with everyone. And today I'm going to talk about the Elastic Cloud. We're going to compare the new experience of running Elastic Cloud to the experience that, it's almost like going from Camry to Telstra. As a Camry driver, I wanted to compare the sort of the old traditional way of running Elastic Stack as, true and tested experience with the new way Elastic Cloud is built and the new opportunities is actually allowing its users to implement. So I wanted to start today's presentation with a quote. And today we're going to talk about things changing and improving as small incremental steps that make the end results more polished, easier to use, and often unlock completely new use cases, whether planned or unplanned, with various consequences along the way. So this is the quote of the day about the progress. And I was looking for an analogy to contrast how the new Elastic Stack and Elastic Cloud compare with the traditional way we use the Elastic Stack, and tried really hard to come up with the right example. So usually when we're talking about progress, we bring examples of technologies that replace one another, such as steam engines and diesel engines, or propeller planes and jets. But to correctly present the new developments in Elastic Stack and Elastic Cloud, the right analogy would be between two things that are both fit for purpose and modern, without one completely replacing the other. And the analogy came to me while driving my Camry. I'm a Camry driver, and seeing Teslas in the traffic around me. So I'm a Camry driver that is really happy with how my car works and how I'm able to use it to go shopping, go to school, do school drop-offs, and so on. So on the outside, the two look very similar, right? Four wheels, seats, steering wheel, even shape, right, of them is very, very similar. On the inside, they're quite different. So batteries, electric motors, internal combustion engine, it's quite different on the inside. So while both can be used to serve exactly the same use cases, right? Moving from Camry to Tesla opens up a whole lot of new opportunities, for people actually who are willing to do that and pay the price, such as, not paying for petrol, being more environmentally friendly, using the autopilot to help me, help them drive long distances, being, a quieter option and safer, and many, many more other options. So for today's presentation, I would like to contrast the way we think about the current way of running Elastic with the new capabilities, the new Elastic Stack and the new Elastic Cloud open for us, with the comparison of owning a Camry versus owning a Tesla. They achieve the same outcomes, but on the inside, the new Elastic Stack and Cloud has completely different features that open a whole lot of new exciting possibilities. So as a reminder, let's do a bit of a recap on how the existing Elastic Stack is behaving and is being used in few key areas. So this is our, beloved, well-known, trusted, and very popular Camry, so to speak, right? This is how hundreds of thousands of Elastic clusters are used around the world. So a lot of clusters that are used to collect telemetry data, logs, metrics, traces, and uptime are deployed with two or more storage spheres, namely hot warm. All right, so hot warm is a very common deployment pattern that can utilize fast hardware for ingesting and analytics of the most recent telemetry data in the hot tier. The warm tier uses cheaper and slower hardware for older data that basically needs more searching, it doesn't, the data is not being ingested into the warm tier. And it allows or creates an option for more economic long-term data retention compared to the hot tier. So we typically see hot warm clusters used for telemetry and security data collection and retention for typically up to 60 or 90 days. And then the data will be offloaded into offline snapshots and just retained on a per need basis. So this particular cluster, as you see, that you see here, is configured for ingesting 1 terabyte of log data and retaining for the overall period of 90 days, right? So it's 52 servers, or about 6 to 10, 12 CPU cores, 8 CPU cores, 64 gigabytes of RAM, each with sort of hefty disk space to accommodate for the ingested data. So traditionally, telemetry data is kept in indices named after the collection components, such as file beat, metric beat, APM. Vast majority of deployments utilize one primary and one replica shards, the cluster is monitored and scaled manually by adding more compute and storage capacity to the cluster. In a very similar fashion, the cluster can be upgraded by rolling in new versions of the nodes, allowing the data to replicate, and then removing the old nodes, right? So this is how we traditionally scale and manage telemetry or time series data in Elastic Stack. Traditionally, the time series data was put in indices, and early on, people relied on periodic rollovers to create new shards, for example, daily or hourly shards. This often results in somewhat uneven shards because Ingest can look differently between days. For example, you can get a normal day and then Black Friday event that produces a lot of data. Index Lifecycle Management fixes that in some way by allowing rollovers based on shard sizes. But other problem in the traditional index handling is still there. For example, we're putting all the data produced by various file bits modules into the same index. So Kubernetes logs will go into the same index as operating system logs, firewall logs, and etc. That may result in what we call sparse index, or index having a lot of attributes that only common to part of some of the documents, for example, Kubernetes labels and annotations sitting alongside records that, have firewall and source and destination IP addresses. So this is perfectly acceptable, but we can get better performance for a whole lot of reasons, if we limit the number of such, attributes and permutations of different attributes attached to these documents. So Elasticsearch is a search engine first and foremost. Search is all about speed, scale, and relevance. So speed to get the results immediately. Scale is about the ability to search the data set of any size, provided the right infrastructure. The relevance is about getting the right results most relevant to the question being asked. So these requirements drove the need for the ingested data to be properly indexed and categorized for speedy retrieval, and requires understanding of how the ingested data needs to be parsed. So many data types can be parsed easily using bits modules compliant with Elastic Common Schema, but something new and unusual requires the time investment into understanding the data, developing the parsing rules, and mapping the data into Elastic Common Schema. So we call it schema on write, and it is also known as what we call Ingest tax. And we said it's best to pay the tax up front and once, rather than having to parse the data on every search to get the speed, scale, and relevance and leverage the benefits of Elasticsearch. So this is the traditional way of how we first parse the data and then we ingest it or indexed up front. We typically see clusters used to retain 30 to 120 days of data, with some exceptions. So for longer retention periods, the data can be put into offline snapshots on a cheaper storage and even archived in something like AWS Glacier. So later, when historical data is needed, it can be needed to be searched, right? The snapshot can be restored into the cluster, right, out of Glacier, out of S3 bucket, and into its searchable form. And it can usually be done in a matter of maybe hours or even minutes. But there's a need for the snapshot to be for the snapshot restore action before the data can be made searchable again. And yet, another thing that characterizes Elastic Stack used for telemetry is basically how we structured the ingest tier or the ingest components. So beats, for example, are lightweight agents used by Elastic Stack to greatly simplify the onboarding of new data sources and make data collection task a breeze. But the family of beats is very widely used to collect the data from a variety of data sources. But each source may require a different module and maybe even a different beat to begin with. So for example, metrics are collected using metric beat. Log files are collected using file beat. Windows events are collected using winlog beat, and so on, right? And often we need to install multiple beats on the same server, often adding to the number of other agents already running on that server, such as antivirus, for example. And we see organizations often run into what they call agent fatigue, right? Where servers that run within the organization for quite some time start to accumulate a large number of agents that consume compute resources, require ever-increasing maintenance efforts, and updating and upgrading beats and other agents often requires modifications of files on the server itself, and may require organizations to use third-party package and configuration management tools, right, to kind of keep the order in the large amount of agents that they need to deploy into their infrastructure. So we talked about and we looked at how existing Elastic Stack is used in sort of hundreds of thousands of deployments around the world. It's the true and tested way of using Elastic Stack to ingest your telemetry data. And we mentioned the key attributes of how Elastic Stack is managed. So hot warm architectures, scaling of Elasticsearch, and how we basically scale and upgrade Elasticsearch, index lifecycle management, schema on write. I talked about the beats family, the ingest layer, right? And this is what I wanted to represent as time-tested existing way of running Elastic Stack. So now we're going to basically switch gears and going to see how the new Elastic Stack and especially Elastic Cloud improve and make it a different and a much easier experience, right, in running Elastic Stack. So continuing with the analogy, let me show you around the new Tesla way of new Elastic Stack and Elastic Cloud. So first and foremost, let's look at the first capability I wanted to talk about today. And I want to talk about the capability that's the new way of doing things with Elastic Stack, and we call it searchable snapshots, right? So searchable snapshots dramatically increase the amount of data our customers can retain in the searchable form in Elasticsearch at a much more economic price point compared to the traditional hot warm architectures. So to illustrate that, think of how Google allows us searching through months and years worth of data, as opposed to only being able to search for, say, only 30 days worth of data. So searchable snapshots can really allow you to extend your queries into years worth of data, as opposed to the current 30 or 90 days that the traditional hot warm architectures let us do. Searchable snapshots leverage the object storage made popular by such services as AWS S3 and Azure Blob Store. So it was a big driver for the industry to build cost-effective and scalable solutions, leveraging its ubiquity and low cost. Here are order of magnitude costs, for example, of storing 1 gigabyte of data per year in hot, warm, and frozen storage tiers backed by the object store. So Elastic traditionally supported the object storage for snapshots, but starting from version 7.11 of Elastic Stack, we can now search in the snapshots data directly without having to restore it into the cluster manually. So searching through snapshots allowed Elastic to kind of rethink the cluster tiering architecture and increase the amount of data retained in the cluster at a much lower price point without losing performance where it matters the most. Now, traditionally, let's have a look at the traditional architecture again, right? So hot warm cluster, it can ingest, say, 1 terabyte per day, 52 servers, really big servers. It's ingesting 1 terabyte of data per day and retaining it for 90 days. So this particular example, again, 52 servers, 14 hot nodes, and 38 warm nodes. It's a big sort of infrastructure footprint that only gives us 90 days of retention. Well, gives us 90 days of retention. So here's the equivalent hot warm frozen cluster to ingest 1 terabyte per day and retain it for 180 days. So notice that twice we already increased the retention period, by 100% or twice. So twice the time the hot warm cluster allowed us. So a few things to notice here. So the hot tier does not change, right? It's what we call the windshield of the cluster. This is where the data meets Elastic. This is where it's going to be indexed, stored and searched the most. This is where the most recent data is being kept, and after about 2 weeks, the data is rolled over into subsequent tiers, cold, warm, cold, and frozen. In hot frozen architectures, most of the data is retained in searchable snapshots that are mounted on fewer frozen tier nodes that are far less, they use far less capacity than what we needed to have in the previous example of the hot warm cluster. So in this cluster, the data older than 2 weeks is stored in a much more economical way, and it's utilizing the searchable snapshots and the object storage. So greatly reduce the sort of cluster footprint and the infrastructure footprint, and consequently the price of running it. So now that our snapshots are searchable, we can leverage them not only for data archiving but also for search. So they're not only for archiving. We also have a smart way of unlocking, make these snapshots searchable. So hot frozen becomes the new sort of foundational way of managing the data in Elastic Stack. Other tiers of storage, such as warm and cold, become secondary tools or controls to get the right trade-offs between storage retrieval, speed, and cost, and sort of the overall cost of the cluster. Now, I refer to the searchable snapshots as cold and frozen tier storage, but in reality, the name doesn't do them justice. It just doesn't mean the storage tiers are slow, right? So cold and frozen implies they're kind of slower than hot and warm, but that's not the case actually with the frozen tier that we built, with the cold and frozen tier that we built. So for example, in our cloud, we're using the same hardware in the frozen tier as the hot tier, right? That may sound interesting. The fast disks in the frozen tier, the same NVMe or SSD disks we're using in the hot tier, in the frozen tier, they act as a disk cache for the snapshot data. So effectively querying the most frequently searched data in the frozen tier can be as fast as querying the hot tier. That's kind of the paradoxical way of, frozen tier being can be as fast as the hot tier for queries. And frozen tier also introduces a new way of scaling the Elastic clusters by adding more compute and disk cache to already existing snapshots residing in the object store, right? Remember how we scaled our cluster by adding more hardware and replicating data across more stores in the traditional hot warm architectures? With searchable snapshots, we can attach more hardware to the same snapshots and make them faster, right? That's the new way of scaling. And it's actually a very common way that many other vendors in the industry already use. So it's basically around cheap object store for data storage, and they scale their solutions by adding more compute and disk to control costs and performance of processing, right? So after all, the main way of speeding things up in IT or infrastructure is adding more cache or caching more. So this is effectively what's going to happen when we scale infrastructure that's built on searchable snapshots and frozen tier. So for our customers, searchable snapshots change the dynamics of how we manage or how they manage data in Elastic. And it allows storing much more data in Elastic at a lower price point. So one of the cluster sizing, for example, I did recently, we were able to go from, say, 2 months of data retained in the hot warm cluster to about 6 months worth of data stored in the hot frozen tier for exactly the same price. So it's actually, was quite an interesting exercise, right? So we kind of doing a 3x data retention increase while maintaining the cluster price, the cloud cluster price. So interestingly enough, it was a security use case that allowed the customer threat hunt in 3 times more data. So they've got more visibility into what actually happened in the organization than they were able to do before, which is a big win especially for security use cases. So in summary, searchable snapshots allow our customers to keep more searchable data in their clusters. They lower the cost of scaling to ingest more data and have more visibility across more data sources for longer. So searchable snapshots are, by the way, enterprise license feature that unlocks access to other things in the enterprise licensing tier. So the control plane automation with Elastic Cloud Enterprise and Elastic Cloud and Kubernetes, for example, 24/7 support. So yeah. So that's searchable snapshots. Now let's talk about the agent. So remember how we talked about the agent fatigue and many different beats. Let's now look at how Elastic Agent simplifies ingesting new data and into Elastic Stack and provides a much more simplified and centralized way to upgrade and manage the fleet of agents used for observability and security. So moving data across systems in different formats from different sources is obviously a huge challenge. So telemetry from infrastructure applications and mobile devices, we implement use cases like, search, observability, security, but it doesn't scale to install separate agents, or it scales very poorly trying to install separate agents or edit configuration files on every endpoint. So with Elastic Agent, we can collect logs, metrics and traces, availability data, security, and other types of data from each host in a single unified way with just sort of one thing to install, configure, scale and secure, right? So it's become single agent for everything Elastic. Elastic Agent is the new sort of generation of beats that comes in the form of a single agent, can be configured, upgraded remotely with ever-growing number of modules becoming available. So we're working towards reaching parity in the number of existing integrations that are currently supported by the Beats family. Now, Elastic Agent is kind of leveraging Beats to some degree, so it's not a very complex task to start porting the modules, and it's already happening. So it's basically It's a logical extension or continuation of the beats family. So the agent kind of inheriting from beats and making the beats sort of making the handling of the beats agents really sort of more optimal. So Fleet Server is the new component in the Elastic Stack that is responsible for management of agents installations. So once configured, the agents can sort of already can start sending data directly to Elasticsearch. And different groups of agents can be configured with different policies and modules to perform sort of different types of data collections based on the use case on a particular host. So there's no need to to SSH onto the box again to change the config files. All the configuration changes can be pushed to the agents remotely. So central management and upgrades. Kibana is used with Fleet and Agent to show and help configure the agents with the available data models. So it's a kind of a one-click configuration. So you kind of select the module, you add it to the policy, and the stack will automatically push that configuration to the endpoint. So previously, our users had to use configuration files to set the modules up. With agent, the configuration can also be done remotely in Kibana and in a graphical format. And again, sort of push to the agents using Fleet Server. Fleet Server gives users the ability to deploy agent upgrades and policies across thousands of agents with one click at runtime through a user-friendly web user interface, and it's part of Kibana. The new agent is not only there for observability data collection, but also for security. It's the same agent that is part of what we call limitless XDR, right? So it's the detection and response, which allows both detections and the response to threats, such as it can do things like host isolation, for example, or run OS query, for example. So it's one agent for all the Elastic data collection. It's not just observability; it's also security. So in security, Elastic Agent provides the foundation for data collection, prevention, host response actions, and the security solution provides the UI and the foundation for detection and response workflow for various security operations teams. So good thing is now we have one agent kind of tick all both boxes for observability and security. So the Fleet setup is already available in Elastic Cloud, by the way. So if you're an Elastic Cloud user, you can simply deploy the agents where they need to be, point them at your Elastic Cloud cluster, and start streaming data into Elasticsearch, as well as you can also protect your deployments. So in the future, we're planning to allow pulling data directly into our cloud from all the major cloud providers, sources such as AWS, CloudWatch, and Firehose, by sort of supporting cloud deployment of beats and agents. So it's fully sort of agentless cloud-to-cloud data ingest. So to summarize, Elastic Agent is a single component that will take care of the data collection for observability and security. It can respond to threats. It can basically help you triage those indicators of compromise. It can be configured remotely using Fleet and Kibana in sort of very few simple steps. So it's a big change to how things were done around sort of the agent deployments and collection of data. Now, remember I was talking about ingesting telemetry data and dealing with indices, shards, Index Lifecycle Management? Well, you'll be pleased to know that we're now introducing a new level of abstraction to hide away the complexity of dealing with those with shards and indices, and we're introducing a concept called data streams. So data streams will still use indices and shards under the covers, but they allow a much easier handling of time series data that is only sort of appended to indices. So time series data is special. We're introducing a new abstraction specifically built for handling telemetry time series data called data streams. So working directly with shards and indices had a few drawbacks, if you remember, sort of when I did our recap. So first, the creation date of an index is not a good indicator of how big the index will be. It may be very different on Christmas and Black Friday, right? Or even worse, when you suffer a DDoS attack, that should not result in differently sized indices, or in worst case, even affect your logging and monitoring infrastructure. So the solution to this is rollover, that allows you to roll over an index based on size and number of documents. Another issue is sparsity of data and index mapping explosion, right? So if you index all your data into very few indices, for example, only file bit dash star, right? You will end up with many different fields once you index from different data sources like Nginx logs, SMTP logs, or auth.log. Uh, you know, it actually means that you might end up hitting the 10,000 mapped fields per index at some point. And it can also mean that the data structure cannot be compressed as efficiently as it can be due to the sparsity of data. So here, data streams allow more fine-grained segregation of different types of data, putting them in separate underlying indices and avoiding sparse mappings. So, how about combining rollovers of data together with dedicated indices for certain data? And how about not worrying about life cycle of those, right? This is basically what data streams allow you to do. And you'll notice that a lot of Elastic Stack components like Fleet and Beats, they already support and they already use data streams internally, even though it is fully hidden from sort of the end users. So you don't have to deal with any sort of additional complexity. So, data streams, they're already there. So to recap on what data streams are, they're a higher level abstraction that hides away the underlying indices, rollover policies, sharding, etc. So what the producers and consumers see is just a data stream, right? Very similar to an alias. So at search time, one of the properties of the query, most oftenly used is timestamp. And the timestamp is used to federate the query only to relevant underlying indices, searching multiple indices or multiple cluster nodes at the same time. Now, indexing the time series telemetry data is always done by adding the newest documents to the most recently created index. So at indexing time, the data stream acts like a write alias to the most recently created index. And as the data basically fills up the index lifecycle management takes care of index rollovers and movement of data between tiers. It basically takes care of snapshotting the data at the right points. For example, if it needs to push it into the frozen tier, it attaches and configures the searchable snapshots on cold and frozen tier nodes. So it may require some initial tuning to set the right rollover periods, but beyond that, index lifecycle management and data streams should take care of the rest of the remaining aspects of data management in the cluster. So a couple of things to summarize about data streams. Now, Elastic Stack components, namely Agent and Beats, now support data streams natively. Data streams, they increase the efficiency of storage and query performance of Elastic Stack by eliminating the sparse mapping problem, among other things. And data streams make the ingest easy and a great fit for time series data and searchable snapshots. So that's data streams. Let's now switch gears and zoom into the new exciting capability in the cloud called autoscaling. So to better explain it, it is easier to describe life without it, right? Whenever I had to set up a new cluster, I always felt nervous to ensure we try and calculate the amount of compute and storage needed for Elastic clusters to do their jobs. As accurate as our estimations tools are, the reality very, very often is quite different from the assumptions we made when we designed the infrastructure for a cluster. And as a result, our clusters were either oversized or, heaven forbid, undersized for the data ingest. And we always needed to spend time to monitor the resulting performance and make adjustment as we went. That was laborious, that was iterative, and sort of often error-prone process. So autoscaling, with autoscaling, life is frankly so much easier. So let me explain how much easier that's going to be. So all I need to do as a customer right now, or as a consumer, is to define the initial small clusters to start landing the data. And I basically need to set the autoscaling to go into the index lifecycle management settings and configure the desired retention periods for my data in different tiers, and I'm pretty much done. So once the cluster approaches the storage thresholds, Elastic Cloud will orchestrate the cluster change to accommodate for the growing data. And it will respect the limits I set earlier to ensure it won't, I won't be surprised with the bill for the auto-scaled cluster. So it actually always going to respect the limits that I'm going to set up for the different tiers to auto-scale. And as the first index approaches the need to migrate to this the storage tier that doesn't exist, for example, the first time we need to move a shard into the cold tier, the nodes of the cold tier will be created just then. So imagine not having to pay for capacity that will only be required 90 or 120 days from from the cluster creation time, right? This is basically cluster infrastructure in the cloud created on demand, on the spot when it's actually going to be required. So that's auto-scaling, right? That's how easy it is. Set up a small cluster, set up index lifecycle management policies, set up auto-scaling limits, and you're done. That's it. The automation will take care of the rest. So to summarize auto-scaling, I can describe it as let your data define your cluster, right? So don't guess, don't spend too much time on sizing, create a small cluster, set up the auto-scaling limits, think about our index lifecycle management, and you're done. Just let the data define your cluster. All right, so additional exciting feature is what we call schema on read, right? So it comes to solve a very interesting, very interesting problem that we had for a very long time. And it comes from the fact that knowing your data and parsing it at indexing time is the way to go, obviously, is priceless. This is what makes Elastic Stack so incredibly fast. And in the long run, schema on write is the right way to go about sort of managing your telemetry data. But sometimes we need to be able to parse the data at search time, especially with new and unknown data. So schema on read and runtime fields allow us to do just that. So we can land the data into the cluster as is without thinking too much, right? So we've encountered a new data source, let it flow into the cluster as is, right? Define the fields that are parsed at search time. So just work with the data as you become more familiar with it. Then use these fields for transforms, aggregations, Kibana visualizations. They will all work as basically in exactly the same way as you use schema on write fields. And then once you're done, once you're certain that this is what we need, this is what I need, these fields work, shift them left, meaning turn the same expression to be evaluated at ingest time instead of search time, or just with sort of very, very little change, just make it into schema on write again. So start with schema on read, shift it left, make it schema on write. Exactly the same scripting expression. So runtime fields bring a lot of flexibility to the stack. So for example, around adding new logged sources. So you may not know all the fields, and experimenting and iterating on the data after it is in Elasticsearch would be easier. And when one of our data sources changes or starts outputting a new kind of message, we can quickly respond and be able to extract and identify these fields, right? And this can be quite valuable. Or maybe we just need to look at the data differently, right? Let's just look at, calculate a different value instead of the original value ingested. So we see so much potential for building new ingest and enrichment workflows where you're using the data, add a field directly from Discover, or where you're building a visualization in Lens, right? So right where you need that new field, you can just click and add this new field in Lens or in Discover. And it goes even deeper than this. So imagine shifting your entire workflow to bring in all your logs and then move right into the frozen to your searchable snapshots. Now you have the data collected centrally, and you can decide later to use runtime fields to query and begin indexing only the data source and fields that you use regularly, right? So it completely changes the way we kind of think about ingesting data, right? It's more schema on read, land it as is, work with the data in Elastic Cluster using runtime fields, and then shift left what's important, right? So start basically parsing the data only when you're absolutely certain about what you're gonna need. So to do this, we introduced a new field type, as I mentioned, runtime fields. So think of this as a regular field that is defined by a script, a regex, or a grok, or even dynamic lookup. So the field is evaluated at query time, but otherwise looks and works just like a regular field. So searches, aggregations, etc., they're all seamless, right? They obviously they don't see any different, right? It's just a field that behind the scenes is being evaluated as a script. So you can define this in Elasticsearch mapping or provide the field definition along with your query. You'll even be able to say, hey, configure this runtime field for all my historic data and start indexing it going forward so that you don't have to leave all data behind or suffer with slow query performance forever. Because runtime field effectively, because the script is evaluated at search time, right, there's going to be it's going to consume it's going to need CPU to parse the data. So there is a performance impact. So schema on write is the way to go going in the long run, but schema on read can be quite valuable at times. So to summarize the runtime fields for you, they're a good fit for getting started with new and unknown data, adapting to changes in the existing data, changing the data on the fly without altering the ingest processes, and fix problems and errors in the data quickly. Right. So there's a new place for runtime fields. So there's more stuff, there's more things, there's more new exciting things and features in the new Elastic Stack and Elastic Cloud. I didn't want to overwhelm you with all of them, so I just, I had to go through the process actually deciding what actually it's going to make the biggest difference in people's lives. And this is what I decided to kind of bring up today. So we talked today about searchable snapshots, Elastic Agent, new Elastic Agent. We talked about data streams, autoscaling, and we talked about the runtime fields. But with only those particular features, we can start painting the bigger picture, right? So we looked at the new capabilities in Elastic Stack and Elastic Cloud. We can start seeing the new way of how Elastic Stack and Elastic Cloud can be used together, right? Let's have a look at our Tesla. So we discussed the parts of the new car. Let's have a look at how the use cases can be implemented. So first of all, we can stop thinking about initial sizing and hardware, right? The cloud will take care of everything, right? As kind of ambitious as it sounds. So you can set up your ingest with the agent and fleet. You can deploy the right modules with one click in Kibana. You can create the cloud cluster just to land your first data. And while you do that, you can enable auto-scaling and set the range, how far it should scale your cluster automatically. You can also define how long the data should be kept in each tier. So start simple, just define the cluster as hot frozen. Hot tier to land the data, visualize it in Kibana, run alerts, machine learning, anomaly detection. The frozen tier should take care of the long term. Think about how long the data is needed and what it can do for you in 6 months or maybe in a year from now. So this is what searchable snapshots can do, right? Then as things become busier, deploy more agents, ingest more data. So watch autoscaling take care of the cluster growth and watch how it's going to create new storage tiers just in time for them to be productively utilized. So you're not paying for them when they actually sit idle. So monitor and observe your cluster with another small monitoring cluster. Set up alerts to inform you when your attention to your main cluster is needed. All right. So this is where things are starting to kick into a high gear. So your cluster is working now. So keep ingesting data. Tune the Index Lifecycle Management. Add more frozen tier nodes to make it faster. Right. Searchable snapshots allow you to retain a lot more data without breaking the bank. Right. So we're now talking about the ability to retain years worth of data in searchable snapshots. Now, runtime fields. Runtime fields can help you deal with changes in your data. They can help accommodate ad hoc requirements without changing the ingested data. So the scheme on write is always there to ensure the speed, scale, and relevance of searches in the Elastic Stack. But runtime fields and scheme on read can ensure your stack remains fit for purpose and adaptable to changes in data and sort of changes in your requirements. So this is the story. This was my story, how new Elastic Stack and Elastic Cloud provide a completely new way of searching, observing, and protecting your environment. And I hope I was able to explain the Camry Tesla analogy. All right. So I doubted myself at times, but I think the story came out okay. So yeah. So again, the time-tested way of running Elastic is how the new features in Elastic, they create the new user experience for our users. I wanted to really say that they both can get you to the supermarket, but how they're doing it, how they're going to do it, and with what effort you need to put into it is going to be very, very different. So all these features, again, that really going to make the difference, right? Really differentiate our Camry and our Tesla. Our searchable snapshots for cost-effective long-term data retention. We talked about Elastic Agent and Fleet, simple single agent to observe and protect. Data streams to simplify telemetry data management. We talked about auto-scaling to remove the sizing guesswork and make the cluster grow with your data. And we talked about runtime fields to provide more flexibility to handle new and changing data without having to modify your ingest processes. So few things to take away with you. So, it's almost like a call to action, right? So first of all, we talked how Elastic Cloud is the make it easy button in Elastic Stack. So if if you're running things on premise, think what Elastic Cloud, autoscaling, and automated orchestration of your cluster changes can do for you. So think about, can you sort of use Elastic Cloud for your next sort of observability or security or search project? Then talk to us about searchable snapshots. Searchable snapshots are a game changer in terms of, the total cost of ownership and the ability to retain more data in Elastic Cluster. And, the question to ask is, what does having more data searchable mean for your use case? Does it mean you're going to be able to threat hunt in 12 months worth of data versus only 2 months, right, for the same price? Whether it means you can retain your logs for 2 years instead of only sort of 3 months. What does having a lot more data searchable mean for a use case? And the third thing is basically start experimenting or look at Elastic Agent as the new collection mechanism for anything observability or security in your environment. And we call it the industry only limitless XDR for a reason, right? So it's a way of, new way of basically leveraging Elastic resource-based pricing for observability and security. So this was the end of my presentation. How are we going with questions?